Okay, so the question of the day is the distribution of gummy bear colors the same for Haribo gummy bears versus Great Value gummy bears? Great Value is the Walmart brand, right? So have bags of each, and I counted up the colors of each, and that's what you have in the table, okay? So you can see the 5 different colors, the totals, and the brands, right? So let's just stop and think for a second. How many samples do I have here? 2 samples. What are they? Haribo and Great Value, right? How many variables are we talking about here?
5.
Well, but they're all one category. What are they? Colors, okay? Colors. 1 variable. All right, so this test for homogeneity deals with 2 or more populations, but only 1 variable. All right? 2 or more populations, but only 1 variable. So we'll differentiate those more later. However, here it is. Now, in total, what proportion of gummy bears examined were red? How would I find that?
Do the total proportion of red divided by the total of all.
The total, right? So 51 over 167, right? So let me give you the short version of that. It comes out to 0.3054. If I did the same thing for green, it would be, what, 22 over 167? That comes out to 1.1317. So I'm just going to fill these in because it's not something you're going to do every time. .2216 and then 0.1916. All right. Can you read it?
Yeah, I think.
You can sit closer while we do these if you need to.
It's okay.
You like squinting?
Yeah.
All right. Okay. Now, complete the missing expected values below, keeping in mind the proportion of each calculated above. All right, so when we do expected values with 2 populations, 1 variable, here's how it works, okay? To find your expected counts, here's how it's going to work. It's going to be row total times the column total divided by the table total. So done the first 2 rows for you, but like for yellow, Haribo yellows, I would do so what I'm putting in my calculator, do the row total, it'd be 25 times 63 divided by the table total of 167. Okay, so row total, column total, table total. And that's how you would find it for each missing, or each box in your table. So that gives me 9.4. So if I did that for Great Value, what am I putting in? I'm going to be row total 25 times 104 divided by 167, right? That gives me 15.6. Orange, I would do 37 times 63 divided by 167. Gives me 14.0. 37 times 104 divided by 167 is 23. 32 times 63 divided by 167 is 12.1. And then lastly, this one comes out to 19.9. Okay, so what are we looking for with our expected counts? Do you remember? When we do our conditions?
So if we did random.
Good. Well, with the expected counts, they have to all be greater than 5, right? And so, are they all greater than 5?
Yes.
Yes. Now, you would not need to rewrite this when we do the problem. You would just say, see the table. Because you did the work somewhere on the page, you're good. Okay? So, we're just making a mental note. All are greater than or equal to 5. We're okay. Now we're going to dive into the 4-step process on this. I'm going to show you, really, honestly, a lot of what's changing is the verbiage. How do we explain our null and alternative? And there's a little difference in how we input in our calculator. So I'll show you that. Okay. So, when we do our hypothesis, we are looking at the color distribution between the two brands, basically, right? So my null is always going to be there's no difference. There is none. So we say there is no difference. In the color distribution for hairbow and great value gummies. Or gummy bears, how are you going to say it? So if that's my null, what would the alternative be? There is a difference. Good. Yep. There is a difference. And this is where I could put in the ditto marks. By the way, we only use the ditto marks in our hypothesis statements. Okay, we don't use them further on in the question, in the conclusions. We're not that lazy. We're not that lazy. I don't know who the guilty party was in this class, but significance, 0.05, otherwise stated. All right, name a procedure. Chi-squared test for homogeneity. Yeah, you got to learn how to spell it. You'll be fine. Homogeneity. Do not abbreviate. Huh? Don't abbreviate. Come on. It's a different test than goodness of fit. We have to enter it differently in our calculators. Yes?
Can we just put square test?
You can't just say chi-squared test. Or x squared. It's chi-squared.
Could we put, was that something for the other one?
No, the other one's chi-squared goodness GOF. They're all chi-squareds.
But with the weird X, right? Because that's the 3 set?
You can, yeah. You can say chi-squared homogeneity.
Okay.
I'm just saying don't abbreviate homogeneity. You can learn how to spell.
The X is curvy.
It's just an X. Nobody's going to judge your curves on your X, okay?
Is it curvy or is it not?
I make mine curvy. You do you, boo. It's just a capital X.
Well, I didn't realize that that's just how you write X. Sorry. I thought you did it on purpose.
All right, checking conditions. Nothing changed here except we have 2 populations. So, random, were both our samples random?
Yes.
Yes, okay. So both samples randomly selected. Since we're talking 2 samples, bless you. You want to make sure you differentiate the 2. By the way, it could be up to 4 or 5 samples, by the way. It's not just limited to 2, but you would treat it all the same, okay? 10%. Now we have to check 10% of each type, okay? So we had a total of 63. So 63, is that less than 10% of all Haribo gummies? I think so. And then with the great values, we had 104, which is probably less than 10%. Great value gummies. Fair assumption, right?
Yep.
And then the third, large counts / expected counts. We already discussed that, right? So I'd mention it here. Expected counts all greater than or equal to 5, and then I would say see table, because that's where you did your work. You don't need to repeat the work, though. Now, formula didn't change. It's exactly the same. You don't have to write it. I'm just going to remind us of it. It's the sum of observed minus expected squared over expected, right? But we just now have, what, 5 times 2, 10 different values to add up. Do you have to write all 10? No. You just need to write 2, the first and the last. Okay? So as far as showing work, here it is. So if I go back to my table, I have it side by side here. Okay. Observed was 20 minus expected. That was that first top left-hand corner of my table. And then I would do plus dot, 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 and then the bottom right corner. This was 19 minus 19.9. Now I'm going to show you how to put this in your calculator in a moment, so I'm going to skip that technical part for now. But degrees of freedom, you need to know how to calculate this. Although the calculator will give it to you, it could easily come up on a multiple choice, right? So you need to know the process. When you do degrees of freedom, you're going to take the number of rows, subtract 1, number of columns, subtract 1. Do not include the totals. So how really it boils down to how many colors did we have? Rows is our colors, right? So it was 5 minus 1. Columns is how many populations? We had 2. So 2 minus 1. So really this is a 4 times 1, so my degrees of freedom is a 4. Picture, chi-squared is always right skewed. It's always right tailed. And for the sake of this example, they're telling us the chi-squared comes out to 2.93. It's really actually a pretty low chi-squared value. So a lot of our curve gets shaded in, I guess you'd say. So what would you expect the p-value to be like? Pretty large p-value, right? Okay, so we're just rewriting here. 2.93. The p-value it actually comes out to 0.57. Can you believe? It's a very large p-value. Alrighty, now we're good. So we can write our conclusion. We can say since 0.57, that's much greater than our alpha, right? So what are we going to conclude here? We failed to reject, good. Failed to reject the null. Then what? Yeah. We do not have convincing evidence that, and then go back to your alternative. What do we say? That there is a difference in the color distribution between Haribo and Great Value gummy bears. Okie doke. Now, stop and think, okay, how is this different than chi-square goodness of fit? Let's go back to goodness of fit. And there's homogeneity. All right, goodness of fit was one population, one variable. One population, one variable, right? Colors of the M&Ms or colors of the Skittles, right? Homogeneity is two or more populations, but still one variable. We just happened to compare two brands of gummy bears. Are there other brands we could have compared? Sure. But still one variable of color was our deal. That's homogeneity. There is a third. We'll get to the third, but before we do, let's summarize this one. All right. It's not much to write up here. There is no difference in, okay, put context here. Whatever it is, color distribution, I don't know what it is we're comparing. Depends on your question. For population 1 and population 2. And then it's just a repeat on the next one. There is a difference. Alrighty. Expected value for a short reference, here it is, row total times column total all over the table total. And all this gives you the same thing on the conditions, nothing changed there. All right, so it's summarizing here the difference. Goodness of fit is one sample, one variable, right? Homogeneity, two samples, one variable. But we're still doing the state plan do conclude. Conditions are pretty much the same. Calculator will do most of the work for you. All right, now let's look at this example. Social scientist selects a random sample of 25 freshmen, 25 sophomores, 25 juniors, 25 seniors from various high schools across the state of Kentucky. Each student was asked if they preferred in-person or remote learning. So here's the results. All right, there's our table. So let's stop and think. What's the variable here? Learning preference, okay? This is our variable. If we have to generalize it, we say learning preference. They had two choices, right? And then the rest of this would be for populations, right? And that's okay. It doesn't really make our job that much harder. All right? So let's just practice for a second. What would my null hypothesis say? Good. There is no difference in what? Good. In learning preference for freshmen, sophomore, juniors, and seniors in Kentucky. So the alternative then would be, there is a difference, right? Now it says show the calculation of expected counts for the remote senior cell, but then it says then provide a complete table. So let's just do the whole table, right? So remote, in-person, freshman, sophomore, junior, senior. Now, they were not very kind to us. They did not total this up for us, but we can do this. Because they told us it's 25 in each class, right? That gives us a total of 100 in the table. So really it's just a matter of totaling our rows, and that comes out to 44 remote, 56 in person. Okay, so as I work these out, I'm going to do, for this first box here. Remote freshman. Let's think about that. We would do, what, 44 times 25 divided by 11. What'd you get? Oh, divided by 100, not 11. What am I saying? 100. Tabletop 11. I knew it was going to be 11, so I said it too soon. All right. So then let's move over to sophomores. We do 44 times 25 divided by 100. Is it sounding familiar? They're all going to be 11s, aren't they? Yeah. Since all of our class sizes are exactly the same, it works out really nicely. So then the in-person freshmen, let's see, 56 times 25 divided by 100, sorry, 14. There you go. Is it going to be the same each one? Yeah, okay. All right, then it says calculate the chi-squared statistic. So let's just show our work for a second. We'd say chi-squared equals observed minus expected squared over expected plus ... Then go into the last, so I'm just doing the first cell here, and then I'm going to do the last cell of my table down here. 10 minus 14 squared over 14. And then I'm going to let my calculator do the work. So I'm going to write on my screen here the steps as you try them in your calculator, okay? So you're going to have, what we're going to utilize in our calculator is a matrix, where it actually builds a table in our calculator, and we're going to put the observed counts in the table. That's all we have to enter is the observed. We don't have to enter the expected. It'll do it for us, all right? So to get to the matrix table, what you're going to do is hit alpha, zoom. So when you hit alpha zoom, it's going to say, okay, how big a table do you want, right? Alpha zoom. How many rows do I need? 2 rows. How many columns do I need? 4. We're not counting the totals, so I'm going to do a 2 by 4. And what we're going to do is enter observed values. All right? Algebra 2, you may have done these before. Okay. Once they're entered, you're going to have to name it. All right? Once they're entered, you're going to hit stow, and it's going to put a little arrow on your screen. So look for the stow button. It's right above on the far left column of your keyboard. You see it? If you hit stow, and then we're going to name it matrix A. And the way to get there is we're going to hit second and look for the button that looks like this, x to the minus 1. That's the matrix menu. And then hit enter. Hit enter to save it, and all it's going to do is repeat the values that you just put in there. We okay? It's a lot of keystrokes, I know, but once it's in, it's no biggie. It stores it as matrix A. From here.
I thought you meant alpha. I was confused. They said A.
From here, we just go to our stat test screen, okay? You're going to go to stat test, and you're going to scroll down till you see the chi-squared test. Not the chi-squared goodness of fit, but chi-squared. So see, now, on this screen, it's going to say, okay, where's your observed? Where's your expected? All right, it should default to say A and B, does it?
Yes.
All right, leave it alone. We named that first one A. It will generate B for you. You don't have to enter that. Then you go to calculate, And there's my chi-squared. So chi-squared comes out to be 14.61. If I wanted the p-value, it's on my screen for me, as well as degrees of freedom. All of that is in my output. That would be chi-squared.